Hello again, everyone. Third session of Advanced Strength of Materials and Generalized Hooke's Law. So L2 is more than L1, but if we call this width D, D1 and D2, D2 is less than D1. So we have S strain in X direction, which is positive, and we have S strain in, let's say, Y direction, which is negative. And imagine if it's a 3D body or material, we have a strain in Z direction as well. All because of this sigma X. S strain is in one direction, but S strain will happen in all three directions, X, Y, Z. And this is how we calculate S strain in.
Just a quick question, excuse me, sorry to interrupt you. Why we have gamma divided by 2? Because in the original equation we only have tau xy sinus 2 theta, but here is gamma divided by 2 sinus 2 theta.
No, I think this is the expanded version should be correct.
Because we were supposed to just replace the sigma by epsilons. Is it correct?
Sigma by epsilons?
Yeah, the same equation for the sigma that we had in, for the rotation. If we replace the sigma with epsilon.
As far as I remember, we have an equation for S strain transportation. You are not supposed to do for S stress. The equation for S stress and S strain shouldn't be same as far as I remember, but the format and the style of the equation that we already shown is completely correct. Do the math and compare the final outcome with this one.
Okay,
it should be okay.
Okay, thank you. Sorry.
No worries. If you do this and you see any inconsistency, please bring up this discussion in the next session. Okay? Nothing?
Maybe we actually limited the movement in that direction.
What do you mean?
I mean, for example, we put a limitation on the material, on the body to not to move in that direction.
No, there is no limitation. We have a term called S strain contribution. Means that the other two directions are contributing in the total S strain in X direction. Assume that we have a sigma X applying on this cubic body, and we divided this S stresses in these three steps. First step. So we have sigma X. Because of this sigma X, we have S strain in X direction. We call it epsilon prime. And it is sigma X divided by modulo of elasticity of this material. So sigma X, sigma in X direction, no sigma in Y direction, no sigma in Z direction, only sigma in X direction.
I mean, maybe I thought that we would consider the axis X and Y actually in the plane of the cross section. Because it talks about the angle. I thought that maybe we should consider axis.
Do not complicate the very simple situation that we are in. There is a beam here. We have P. We have tau. The easiest way to consider the X and Y axis is the way that maybe I think the whole planet do like this, right? This is X, this is Y. You can consider this X and this Y. You can draw something like this and consider X and Y with the 30-degree theta here. Everything is doable and possible, but you're just complicating the situation. Take the easiest and most straightforward way that we usually do when we consider axis. Plane stress, and it has been clearly mentioned here, it's in the state of plane stress. And when it says plane stress, it means that sigma z is 0. And we have uniform normal stresses sigma x and sigma y, as illustrated below. Again, in the question has been mentioned all other stresses are 0, but there is no need to mention this because it's obvious from plane stress condition and sigma x and sigma y. To find A and B, sigma in x direction and Poisson ratio, we can, as I said, we can easily calculate the strain in x direction. Why? Because we know using this as our force times the distance, which is x from here, which is 0 to here, which is AD or A, small a, the maximum length. Same for this side of the bar. We have B at point B, the reaction force or the force RB this is the force. And again, rather than x here, we have small v in different distance from B. So from 0 to maximum BD or small b, we can calculate what m. These two equations are the maximum m1 and m2 because this is the maximum distance. B for this one, A for the other one.
In the Castigliano's formula, we had actually the displacement is differential equals the differential of U and F, force, I mean energy and force. But here it is not that formula. We have both of them.
I think we already solved two equations. Sometimes we have displacement, we are looking for force. Sometimes we have force, we are looking for displacement, right? So you can use the equation that we already discussed in the previous session, and you should at the end of the day, you should have the final answers as we reach now. The explanation has been here, okay? Poisson ratio is usually around 0.5 to 1 here, not minus. And this is a unknown two equation. So when you solve it, you have two answers, but this one is not your answer. This is the right one.
I know, because it explained that we have.
We don't have negative. No need to if this explanation says that we have negative, even this explanation is saying that we have negative. This is the final. Let's choose Poisson ratio 0.8, right?
Yes.
Poisson ratio in 95% of materials is engineering materials is between 0.5 to 1.
Yeah.
So 0.8 is the reasonable one, right?
I think when you consider a direction for a force and then it is positive, the final is positive, it means that you are correct, I think, because you put it positive in the equation and then you get to positive, then it means that it is correct, the direction that you consider.
So a quick note, we have R1 as negative, but as you see here in this equation, R1 plus R3 plus 160 equals 500, right? So it means that these three, R1, R3, and 160 are assumed to be in a different direction compared to 500.